Hello class, welcome to another video of this course. In this video, we are going to study section 4.4, the fundamental theorem of calculus. So here we want to see how we can find the exact value of definite integral without taking the limit of Riemann sum, or in other words, without using geometry or area. If we are unable to do that, how can we find the value for an integral? And also we introduce the fundamental theorem of calculus. So I want to discuss, we saw in this chapter, we started by introducing the Riemann sum, and then we saw that, okay, we use Riemann sum in order to approximate the area under the curve. And then we saw that as we increase the number of subdivision, or in another word, as we take the limit of Riemann sum, then we get a better estimation, and therefore we introduce the notation of integral. Now, if we are given a function like here, suppose you have the position function, right? Position function of an object. That means a function that tells you the location, the position of a moving object. And you have the velocity function of the moving object. Then the relationship between these two is that velocity is the derivative of position function. This comes from physics. But in our objective, we want to, let's say we want to see we are given the velocity function. So suppose we have the velocity function, and this is the graph of velocity function, and we are wondering about the distance traveled by the object from point A to B, right? So if the only thing that we have is the velocity function, not the position function, then we have to evaluate this integral, because the position traveled by the object is the same as the area under the curve. So, and we know that the area under the curve is the same as the finite integral of v of t respect to t, t is time here, from point A to B. And so maybe I draw what I mean. Look, suppose you have a position function. Suppose S is the position function. And you want to see the distance traveled from A to B. So that means you should look at the place of, suppose this is T, this is S. So suppose this is S of A, right? And then you have, for example, S of B, right? And then the distance traveled by this is going to be S of B minus S of I, right? But what if we don't have the formula for the equation of the S? Because if you have the formula for this function, you can easily evaluate S at B, S at A, and then subtract them. But what if we don't have it, and instead we have the velocity function, which is its derivative? So suppose instead you have the graph of velocity function, something like this. So you know what is v of, so you have the velocity function for this. So same thing, look, the area under the curve from A to B. This is gonna give us S of B minus S of A, which is, so this can be obtained here by computing the area under the curve from A to B for the derivative function, for the velocity function, right? And we just learned that that can be obtained by integral. So that area is actually the definite integral of the function, the velocity function, from A to B. And we just know that this is going to give us the distance traveled from A to B, which is the same as the difference in the position function at A and B. And what is the relationship between S and T? So S is a function. S is the position function. V is velocity function. And what is the relationship between these two? V is the derivative of S. What's the relationship between these two? If you take the derivative of S, if you take the derivative of S respect to T, that's gonna give you the V. So velocity function is the derivative of position function. That's the relationship between these two functions. So from here we can get an from here we can get generalize it and get an observation that, okay, if you want to find an integral in general, so okay, so look at this picture. Suppose you want to find an integral of a function from point A to B. Suppose you want to find this, right? So what graphically that means, suppose this is the graph of f, and then you want to see, so that integral is the same as area under the curve, right? So it's not easy to find, I mean, in general, it's not easy to find the area in the curve. Yes, we can do the limit Riemann sum, but what if we don't want to do limit Riemann sum? What's the other way? The other way is that, think about this. If we have the function that give, so the point is that if we can find a function, let's denote it by capital F. Let's say if there is a function capital F such that the small f is the derivative of this one, like here. Here, what do we have? Velocity is the derivative of position function. So suppose we can find a function that this f is the derivative of that function. Then we can simply say, okay, if we can find function f such that you take its derivative and it's going to give you function f, then in that case, we know that this can be obtained by f of b minus f of a. You see that? So it's like, instead of, by the way, this is called anti-derivative. So again, capital F in this here is called antiderivative. A small f is called the derivative. Why? Again, look, here is the relationship between these two functions. If you take the derivative of that original function, you will end up by f. That's the relationship between these two. So whenever you have this setup, then this is called derivative function. Derivative f is the derivative function, and capital F is called antiderivative. And then this, so the point is that if we have the antiderivative function, or if we can find the antiderivative function, then we can easily use that antiderivative in order to evaluate an integral. For example, look at this example, 4.4-Calculus. It says determine the exact distance traveled on 1 to 5 by an object with velocity function v, and okay. So in this example, we have we want to find the distance traveled. We want to find distance traveled by a moving object from 1 to 5. That's we want what it is that we want to find. And we know that it has a velocity function. So velocity function has the formula of v of t is velocity based on time. 3t squared plus 4t. 3t squared plus 4t. Then the distance traveled on this interval. Okay, so again, look, the distance traveled is gonna be the integral of v of t dt from 1 to 5, right? Now, this is what we need to find. The distance is gonna be obtained by the integral of v of t dt from 1 to 5. So I need to find the integral of, what is the formula for v? 3t squared plus 4t respect to the variable t from 1 to 5. Okay, so if I can find the antiderivative of this function, that's going to be the, if I can find the position function, right? If I can find the position function, then this is going to be just s of 5 minus s of 1. The distance traveled from 1 to 5, it's going to be s of 5 minus s of 1. So I just need to find the antiderivative. So how can I find the antiderivative of position function? So the question is, what is the function that its derivative is 3t squared plus 4t? What was the original function? Then when we took the derivative, it gives us this. So for 3 squared, recall that, maybe I do it here. So recall that you have this formula, that because this is a power function, right? So for power function, we know that t to the power of n is going to be n t to the power of n minus 1. The derivative rule for power function is this, right? So now in here, I have 3t squared. So that suggests me that, okay, whatever was the antiderivative, if here n minus 1 is 2, if n minus 1 is 2, that means n was 3. So here I had 3 cube, right? Because if I had 3 cube, then the derivative of 3 cube, yes, derivative of 3 cube is 3 times t squared. Okay, so the first one is 3 cube. And then 4t, so this is gonna be 40t because the derivative, so it's like, this is the antiderivative. This is the antiderivative function. Why? Because if you take its derivative, take the derivative of t cube, it's gonna be 3t squared. Take the derivative of 40t, it's gonna be 40. And this is the derivative. Okay, so it's like undoing. You learned how to take the derivative, right? Now it's like undo that process. You have the derivative, now figure out what was the original function, what was the antiderivative. Okay, so now we can say that we found s, right? So we need to evaluate s at 5. Okay, so it's going to be 5 cubed minus 4t times 5. That's going to be s of 5 minus s of 1. S of 1 is going to be 1 cubed plus 4t times 1. And then you can just simplify this in order to find the answer. Okay? So the idea, again, is that the distance is the integral of velocity function from 1 to 5. Velocity function has this formula. And we know that this is the same as position function at 5 minus 1, where this position function is the antiderivative of v. So we need to find the antiderivative. The antiderivative of 3t squared is t cubed. The antiderivative of 40 is 40t. So this is going to be the position function. Now just evaluate it at 5 and then at 1 and then subtract them. 284 is the answer. So I think you got the idea. So now we introduce the fundamental theorem of calculus. If f is continuous on the closed interval a and b, and capital F is the antiderivative of a small f. So in this case, the relationship between capital F and a small f is that a small f is the derivative of f. Then we have this relationship in terms of their integral. So I'm gonna write this down. So fundamental theorem of calculus says that if you have continuous function and the relationship between these two is that f, you take its derivative, it's give you the small one, right? So in another words, capital F is the antiderivative of f, or small f is the derivative of capital F. That's the relationship between these two functions. Then the relationship between their integral is that this is the relationship. The integral of a small f, the derivative one, from point A to B can be obtained by the evaluating the original function at A and B and then subtract them. The order matters, f of b minus f of a. Okay, again, what is f here? Capital F is the antiderivative. What is a small f here? F is the derivative. Okay, so let's see a couple of examples. By the way, we use this notation as well. Sometimes you also see this notation that just puts capital F of x, and then it puts something like this, b and a, which means that substitute b and then subtract it with substituting a. So same thing as here, just a different notation. So, for example, for 1/3 x cubed, the derivative is going to be x squared. So in another words, let me show you this example. For example, look at integral of x squared dx from 0 to 1. So we know that by fundamental theorem, we know that this is going to be capital F at 1 minus capital F at 0. What is capital F? So imagine that, so call this f of x. This is your function, f of x. The relationship is that capital F is the antiderivative, or in other words, when you take the derivative of capital F, you get the small f. That's the relationship between these two functions. So the question is that what is this, what is the antiderivative? Okay, so what is the, think about it this way. This is x square. So what's the function? Because this is power function, we know that x to the n, look, I'm going to put it this way. X to the n derivative is going to be n times xn minus 1. So if the derivative part is 2, that means n minus 1 is 2, so n is 3. So that means here it was x cube prime, but x cube prime gives me 3x squared, but I don't have 3 here. So that was why it was multiplied by 1/3. So that's it. The antiderivative is 1/3 x cubed. So we just undo the process to find the original function. So it's gonna be 1/3 x cubed, 1/3 1 cube minus 1/3 0 cube, which is gonna be 1/3. Okay. And then I recommend you to try this activity and then You know, sometimes it's easy to find a basic antiderivative like sine and cosine. Okay, so for example, you know the derivative of sine. Look, for example, if you look at sine, you know the derivative of sine is cosine, right? So if you're given cosine, you know the antiderivative is sine. You know, sometimes it's easy to just figure these things, but sometimes it's not easy. And for example, and you know, there could be many function, not just one function. There could be infinitely many function that gives you that function. But because we are working with definite integral, that's not a, you know, that's not an issue. We can forget about that. And then when we look at other integrals, that's something that matters. But yeah, maybe we do a couple of examples of antiderivative. For example, so that's it. That's the fundamental theorem of calculus, that you have f is continuous and capital F is the antiderivative. Then the integral of a small f is related this way to capital F. Or if you don't like that notation, you can also use this notation. Okay, for example, let's look at this one. Okay, let me show you number 2 exercise. I'm gonna show you number 2 in the exercises. So this is number 2 in the exercises, and the question is find the value of this integral. It's the integral of 1 over x squared respect to x from 2 to 4. Okay. So this is the same as integral of, I would like to rewrite it in the standard form of power function. So we can flip this fraction and rewrite it as x to the negative 1 from 2 to 4. Okay, now, because this is power function, let me recall the rule, the derivative rule for power function. If you have x to the n, x to the power of n, the derivative is n times x to the n minus 1. So if my derivative here, the idea is that this is the derivative. This is the derivative function, and I'm looking for antiderivative. So if the derivative is x to the negative 2, so from here, I can see that, okay, if n minus 1 is negative 2, so n must be negative 1. So here I should have x to the negative 1, right? And okay, but here is the thing. If you take the derivative of, if you take the derivative of x to the negative 1, then the derivative is going to be negative. The sign is going to be negative x to the negative square. But I don't have a negative here. You see, there is no negative here. So that means I need to multiply this by opposite sign. So it's going to be negative x to the negative 1 from 2 to 4. Let me rewrite it. Negative 1 over x from 2 to 4. So negative 1 over, first we substitute the top limit 4. Negative 1/4 minus negative half, and then you simplify this. So it's going to be 4, negative 1 plus 2, so it's going to be 1/4. Okay? So I think this is going to be 1/4. And yeah. And with the same idea, let me also show you this one. Number 3. Let's evaluate the integral of, this is number 3, the integral of, what's the function? 4x plus 10, 4x plus 10 dx from 2 to 9. What is this, right? And so we need to take the antiderivative, right? So the question is, what is the antiderivative of this function? So what does give me 4x? Again, recall a power function, x to the n. The derivative of x to the n is n times x to the n minus 1. What is the derivative here? It's 4x, right? It is, okay, the derivative here is 4x. So that means I'm just looking at the power. If you want, the multiplier doesn't matter. The power matters here, okay? So if here I have power 1, so that means n minus 1 is 1. So n must be 2. So that means I had here 2. So the power element is 2. So antiderivative is a multiplier of x squared. Now, if you take the derivative of x squared, it's gonna give you 2x. But here I have 4x, so it was multiplied by 2. So this was what? This was 2x, but also, sorry. It is x squared. The antiderivative is x squared, right? It contains x squared, but it is more than that. Why? Because for x squared, the derivative is gonna be 2x. But here I have 4x, so there was a 2 as well here. Look, take the derivative. It's gonna be 2 times 2x. So that gives me 4x, right? That is here. So now this is correct. And finally, for 10, it was 10x, because what is the derivative of 10x? Is 10. That's it. And we take this antiderivative from 2 to 9. What does it mean? We first evaluate the function at 9. This is the function at 9, and then subtract it from, evaluate the function at 2. And then just simplify. Got it? So I recommend you to try to practice the rest of exercises, and yeah, then I think you would be ready to do the homework assignment of this section. Thank you for watching this video. I'll see you next time.